So in this video, we're going to look at an example of an acid-base reaction involving something that's a weak acid. The way we usually write acids so you can recognize if they are acids is look for a hydrogen right at the front of it. So in benzoic acid, we see there's an H right at the beginning. That's a signal that this is an acid. And again, bases, not all bases, but many bases are going to have hydroxide ion in them, and that makes them a base. And so here's an example of an acid-base reaction. And what we'll do in this video is we'll predict what are the products of this reaction, and then write out the total ionic equation and the net ionic equation for this reaction. So let's start here. We have recognized that we have an acid and a base. That's the first step often in questions like this, is figuring out what the products are supposed to be. And I can tell you, since benzoic acid, since this isn't on our list of strong acids, we can say this is a weak acid, meaning it only partially dissociates in water. That still means it'll still act as an acid. It'll still donate protons. It's just not as strong of an acid in water, meaning it'll be a weak electrolyte. Potassium hydroxide is a strong acid, strong base, not an acid, because it is a metal hydroxide from the first period. So if you look at the periodic table, you'll see potassium is in the first group of the periodic table. So this is an example of a strong base. Now, what we know is that our proton is going to be donated by the acid, and it's going to be accepted by the base. So if this were a strong acid and a strong base, the protons and hydroxide ions would be completely separated and to just form water. We saw that in the last video. But with the weak acid, we get a little bit different products out of this reaction. Okay, enough talk. Let's go ahead and write out what's the products of this reaction. Well, the proton will get donated and get accepted, so we are going to get a combination of K potassium, so the K plus ion here, will combine with the benzoate ion. You don't need to worry about knowing that name, but you should recognize that there's an ion that's going to form from this. So this will react, and then our H plus and our OH minus will react, and we'll get water. And by the way, this type of acid-base reaction, another name for this is a neutralization reaction, because the acid and the base neutralize each other. Just want to make sure you have that vocabulary. Okay. One thing I've neglected to do is list the states of matter for all these. This is aqueous. This is aqueous. This is aqueous. This is aqueous. So this is something you should be looking out for when there's an acid-base reaction, is that the protons are going to combine with the hydroxide ions to form water. So we get the same product here, but our net ionic equation is going to be slightly different. And let's go through that. So let's go ahead and write out, so this is our molecular equation here. Let's write out the total ionic equation. So that's our next step, total ionic equation, just to understand what's going on here. So our benzoic acid, being a weak acid, does not dissociate. So that H just sticks on to the benzoate ion. That's not a Z, that should be a 7, C7H5O2. So that's still aqueous, it dissolves in water, but it doesn't separate into ions, into H+. Only a little bit of it is H+. So we will write it as combined. So this will stay combined. On the other hand, potassium hydroxide, since this is a strong acid, strong base, not acid, it completely dissociates into K plus and OH minus ions. Now, on the right-hand side of the equation, potassium and benzoate, this is not an acid or a base really, but this will form separate ions, and we'll get more into this at the end of this chapter about knowing whether these will form ions or not. And then water, that should be a liquid, not an aqueous, is our other product. Okay, so we've got our total ionic equation here. So then we can identify the spectator ions here. We have K plus, it's a spectator ion, so that will be eliminated in the net ionic equation, and that's the only one in this case. And that's the main difference, is because we have a weak acid, the H plus, this benzoic acid over here, doesn't dissociate That blue really doesn't show up. Let's try again. This benzoic acid over here doesn't dissociate, and so we keep that together. And so our net ionic equation will still have that benzoic acid in it completely associated together. We'll eliminate the K plus, so we just have OH minus. And then that reacts to form our benzoate ion. So it's lost that proton, it donated the proton, and our water. And so that's our net ionic equation here. And so this hopefully helps drive home the fact that with a weak acid, we're not getting this complete dissociation, and so it'll show up in our net ionic equation. And that'll generally be true for weak acids and bases. Because they don't completely dissociate, in the total ionic equation, they won't be written separately, and you get them sort of sticking around into the net ionic equation. And so that's what makes this a little bit different from the strong acid, strong base reaction we looked at in the last video. Now, one thing I'll mention is we will get to making this prediction, like that this separates. I wouldn't expect you to know that yet, but we will get to it before the end of the chapter, that our potassium and benzoate will form a compound that dissolves into separate ions. Because you need that to understand what's going on with the net ionic equation. But we'll get some practice with acid-base chemistry first, and then we'll look at dissolving things. So our next video, we'll be looking at titrations, which is a way of using acid-base chemistry, or you can do it with other things, but we're going to focus on acid-base chemistry to measure concentrations of species in solution.